Excellent. So it's great that the topic of GI has already been introduced by two previous speakers. It makes my job easier. Let me first of all mention my collaborators. So Sandra is here and speaking after me. And then two other PhD students, Liao Zhang and Hans Li, also worked on this project. They're not here, but they're integral to the results. Right, so the story of GI starts, a long time ago, but I bet that most of you don't know that Kuiper actually thought about a way to make the solar system from GI, not just the gas giant planets. Well, basically you have disk fragmentation, you have these molecular clumps, and then dust can grow and sediment to the center. If the gas then cools and collapses onto the core, you get a Jupiter-like structure. But if it is not able to cool rapidly enough, or the fragment is too close to the sun, then the tidal forces remove the envelope and you get terrestrial-like planets. Okay, so that's a scenario. Well, he's according to the modern understanding of GI, he's made two huge mistakes. First of all, he thought that the solar system can fragment on the scales of 1U. Now, due to cooling constraints, we know that is not possible. We know that disks fragment only at tens of U. I don't have time to explain these curves. This is from a recent paper by Hans Li. But what we've done here is we've looked into how dust growth changes disk fragmentation. It reduces the opacity of the disk, so it makes it easier to fragment. But even with very aggressive dust growth, you still can't really fragment, closer than 30 U or something like that. Okay. His second mistake is that he thought that planets just formed in situ. Of course, at his time, planet migration was not even invented. Right? But now, dozens of different simulations with different simulation techniques all show that planets migrate inwards rapidly within just a few thousand years. So in the middle, for example, there's a paper from Clément Baruteau et al. And you see that planets migrated from 100 U to 20, the inner boundary of their computational domain, in 5,000 years. Okay, and so this is from a paper that we've done a number of years ago now, and that was the first, as far as I know, simulation of GI with dust. And we found that the scheme proposed by Kuiper can actually work. You have dust growth and collapse in the center. One of these clumps was, came very close to the star. It was disrupted. And on the left, you have a surviving fragment, dust fragment marked with super Earth, or SE. So it formed the super Earth Mars planet at 8 AU separation in just 6,000 years or so, I think. So the simulation, the Kuiper scenario can, in principle, work. But there's something else that I didn't really think about at the time. So this simulation actually, so this is from that paper. It it has a number of these fragments that are disrupted and with cores. But you also see that some of them are ejected. Then another thing which I didn't really want to discuss at the time is that if you continue this movie for just a little longer, these two clumps actually merge and you get something quite massive. This is what Oliver was talking about. So you actually also form binary stars here. So in principle, GI is a really powerful scenario that can form many different types of objects. Something new that happened in the last few years. The story was accumulating starting from Ken Rice's paper in 2004 and others. But if you want to understand this better, read Longarini et al. 2024. What we think now is that you may also have direct collapse of dust in your cell gravitating disk. So the gas component doesn't collapse in this case, but the dust component does. So you can then form solid cores that way. And it's obviously quite interesting, not just for GI, but also for a possible connection to core accretion. So the story is that, putting this all together, we now think that in principle, GI can form all sorts of planets at all sorts of separations. So the arrows show what essentially corrected Kuiper scenario is. And the other option for forming small mass planets is direct collapse of these dusty spirals and forming, solid cores at wide separations very rapidly. Okay, so that is going to be really important for my talk. Well, there's a lot of misconceptions, I would say, about GI, which make, I think, many people somehow stop and not think about it at all. And we just continue with core accretion. So I already mentioned the direct imaging result is actually completely consistent with modern GI simulations because it's very difficult to actually leave these fragments behind. So a few percent of planets there now is close to a miracle. It might suggest that many disks fragment and have many fragments early on. The other point to make is that, well, we've heard already yesterday that ALMA disks are quite small and also relatively low mass. But does it matter for GI? Well, frankly, no, because what we're thinking about in the GI phase is very early phase when the star itself hasn't yet finished growing. It's a very highly embedded phase. It's a very short phase. ALMA is not able to observe these disks. ALMA looks at disks which is 3 to 10 million years. We don't know how exactly the disks evolve since that early phase, you see. The other common critique is that, well, GI can only make brown dwarfs or companion stars. I think GI can make those, and I'm sure does, but I think this is too broad a statement. If you look at the microphysics of a model, there are lots and lots of uncertainties, such as dust growth, as I already mentioned, MHD, proper radiative transfer, resolution. So this is from a very recent paper by Yang Ni and collaborators showing, this is, I think, the best paper to date that has been done on actually forming these clumps from first principles, as Nader wanted. And we do find that you can form Jupiter mass fragments in the disk. Okay, now, so yes, this is the largest controversy in the field. What does actually GI do? And I must admit, I used to think only about processes 2 and 3. That gives you planets, all right? And I know a number of people used to think only about 1, okay? But I will argue today that actually both physics and observations, especially free-floating planets and planets in binary systems, tell us that all 3 of these happen, and happen possibly simultaneously, which is the most interesting result. So why physically I think that all 3 of them happen? If you look at the first principle disk fragmentation simulations, such as the one that I was showing on the slides, a few slides back, you will find that the fragments actually form with a range of masses by at least an order of magnitude, just due to stochasticity, mergers, interactions with spiral arms, whatever. So there's a wide range. And that's really important because if you look at what happens with a fragment in your disk, so this is from a paper, my paper some years ago, where I've looked at the fate of fragments. Okay, I'll try to show it on the screen. Oh, I can't see my pointer. Oh, that's fine. Okay, so I just started with fragments with mass between 1 and 16 Jupiter masses at 100 TU, and then looked at what happened. At low masses, what happens is migration, then followed by disruption in both cases. Oh, thanks so much, Sean. So yeah, at low masses, you get basically planetary mass objects. But at high masses, there's a runaway process in which these fragments grow by accretion very rapidly. They cross gap opening mass, which is that line, and then they continue to grow into the massive brown dwarf and secondary star regime. And of course, that all can happen at the same time on the disk. Right, so just to say that we do think that there's some observational evidence for GI being important for real systems. So these are M-dwarfs, gas giant planets and M-dwarfs. This is stars less than 0.2 solar masses, and core accretion really struggles with making these because there's not enough metals. Also, Ruf already mentioned the metallicity correlations that change at a mass of 5 to 10. And it's possible that it means that the more massive objects are made by GI. There's also, I would argue, very strong evidence from observations of a priori outbursts, young protostars, right, still growing by accretion. And one of the scenarios for this, the best scenario, I'd say, is that these fragments actually formed by GI, they migrate, and when they accrete, that gives you a burst. So these are some early simulations from Vorobyov, but please look at the time scale. All right, so these events only happen at very early phase. So GI is very rapid. It's an instability, right? So it works while you have a mass supply and a very massive disk. Right, we talked about this slide already, and the point just to make is that there are really many free-floating planets, right? And it's not clear if some of them are actually bound planets. That's quite possible. I think that must be so. But even in that case, I would say that it's quite likely that these are formed by gravitational stability, because it's difficult to do so with core accretion and with gravitational stability. It's just what's actually predicted. If you put enough physics in your model, including dust growth and a collapse of these cores, you will get all of these planets quite naturally. This is a very nice paper by Gu et al. And we see that planet-planet scattering is not likely to make enough free-floating planets. Right, so the binaries can be a really efficient way to eject planets. So this is from Holman and Vigor, already mentioned in this paper. And if you have a binary with this separation, which is 40 U at this plot, it's circular, then depending on the binary mass ratio, a really wide region of a parameter space isn't stable for planets. If we put a planet there, it's ejected. But the question is, can you actually seed the planets there? And of course, Nader was absolutely correct that we need to include planet formation in these models. You can't just be throwing them there by hand. And in core accretion, it's actually very difficult because, of course, when you try to make these planets, the planetesimals would be colliding at very high velocities, and you don't really form planets there. With GI, it's much easier. And I don't have much time to explain this, but it just shows the field binary population, and this is for hosts of planets, and it shows that planets are underabundant in binary systems, but the interpretation of this could be that they never formed there, which is the standard interpretation from co-accretion, but in GI, it might mean that they formed there, but were rejected. So that would be my interpretation. So Gavin Coleman suggested this quite natural scenario for forming planets in co-accretion. You have, this is your small scale binary, 1 AU or less, and then you can eject planets from this region here, close to the binary, but you can't form them there. So you form them there initially at 10 AU, they migrate in and then get kicked out. Unfortunately, most binaries, of course, have these wide separations. So you are not likely to actually make many planets that way. So our scenario is we start with a gravitational unstable disk around a single star initially, right? There's no binary yet. And you have a number of clumps. And as I said, some of them just more massive than the others. So one of them grows into oligarch, then it grows by accretion into massive brown dwarf and continues to grow. And then in simulations, that fragment migrates in faster. It then runs through the orbits of the other planets and ejects them. Sandra will talk about that for gas giant planets in particular, but this paper is in review, and here what we've looked is what happens with small planets, and we find that they're ejected really efficiently. So here is the growing binary radius evolution in the model. It migrates in, opens a gap, and then actually migrates out, developing some eccentricity. This is the mass of the secondary. It's here on the right. So it grows from few Jupiter masses to 0.1 solar masses or so. And while this is all happening, you eject many of the planets. A number of planets survive as well. So these would survive as circumbinary planets on very wide separations, while these ones actually survive as S-type binaries, S-type planets in a binary. And just to say that in this model, so this is from simulations of just fragments migrating in this disk, constant mass fragments. The referee asked us to look at that in that. And what you find is that low mass fragments, as I said, migrate in very rapidly to the inner boundary of our domain and then just stay there, and they eject nothing. But high mass objects eject many more planets. And the reason for that is that they are unable to migrate so rapidly, they get stuck. And this is where GI planets are as well in the model. And so we eject many. So I'm going to stop here. Thank you.
Sorry, could you go back to the slide where you were showing planets form around one star and the other star plows into it? Right there. Okay, yeah, right. What is the time scale here? What's the time scale for your planet formation and time scale for star coming in?
5,000–10,000 years.
Say again, I'm sorry.
5 to 10,000 years, very rapid.
Oh, you're making it that rapidly. And what is the cause of the second star coming in? What makes it to come in?
Oh, it's called gravity.
Oh, I see. Okay.
It's migration in a very massive disk. I mean, so
because you have already.
Yeah, I mean, this all, I mean, this is a cartoon,
right?
But it's based on the hard dynamical simulations that we've done in 2D and 3D.
But you have used a lot of that material for forming planets, and planet formation is inefficient. You get rid of a lot of material too, right?
So our disk is 50% in mass of a star.
Right.
So GI is very different from core accretion.
That is true.
The migration is much more rapid because the disks are an order of magnitude more rapid. So we push the planets in much more rapidly.
Okay, great. Okay. Thank you.
All right, let's thank Sergei again. Cool.